Hello students, in last class we have seen about the properties of determinants and the exercise 4.2 problems up to 4th one. Now let me come to the 5th problem, that is show that b plus c, q plus r, y plus z, c plus a, r plus b, z plus x, a plus b, p plus q, x plus y is equals to twice of the determinant a, p, x, b, q, y, c, r, z. Now, how do we proceed this? Now, consider LHS. LHS is equals to b plus c, q plus r, y plus z, c plus a, r plus b, z plus x, a plus b, p plus q, x plus y. Now, when you see this problem, you cannot do any column operations because these variables are different, these are different, these are different. But when you see row wise, this is b plus c, c plus a plus b. So I can do the row operations. And one more thing what you have to remember is, while solving the determinants, see that is it possible to make any row or any column elements as 1, 1, 1. That means if it is 3 by 3, see that the elements, all the elements of any row or column becomes 1. If it is so, our problems will be so easier. So once again, I repeat this, that is, while solving the determinants, what we have to do is, see that if possible, all the elements of any row or column make 1. Now, is it possible here? Now let me check it. When I add all these rows, it will become a plus k, that means twice of a plus b plus c, twice of p plus q plus r, twice of x plus y plus z. So here you are getting twice of a plus b, p plus q, r, that is x plus y plus z. So that means I am unable to take the common as it is, but I can take 2 as common. So that method is not working out here. Let me see it. That is r1 as r1 plus r2 plus r3. That is equals to, now r1 as r1 plus r2 plus r3. That is b plus c, c plus a plus b. That means 2a plus 2b plus 2c. So I am writing directly here twice of a plus b plus c. In the same way, when you add up all these three, this is 2p, 2q plus 2r. That is 2 into p plus q plus r. Here, when I add up all this, r1 plus r2 plus r3, 2x plus 2y plus 2z. 2 into x plus y plus z. Now, rest r2 as it is, c plus a, r plus b, z plus x, a plus b, p plus q, x plus y. Since 2 is common in the first row, I can take 2 as common. So by taking 2 as common in R1, because if it is a matrix, we have to take the element common from all the elements. Whereas in the determinants, from the single row also we can take the common. So that is equals to twice of a plus b plus c, p plus q plus r, x plus y plus z, c plus a, r plus b, z plus x, a plus b, p plus q, x plus y. But what is RHS? You have to get the single term. That means you have to do some operations here again. What operations I can do? Now let me see. R2 as R1 minus R2. When R1 minus R2, A plus B plus C, minus C, minus C, minus A, minus A. Therefore, B will be left over. So, I will write as R2. R2 as, that is second row as R1 minus R2, and in the same way R3 as R1 minus minus R3, which is equals to twice of first row as it is, A plus B plus C, P plus Q plus R, X plus Y plus Z. This is, now let me apply this operation. R2 as R1 minus R2, R1 minus R2. A cancel, CC cancel, therefore this will be B. And here PP cancel, RR cancel, it will be Q. I hope you are understanding. P plus Q plus R minus R minus P. R minus R, P minus P. In the same way, X plus Y plus Z minus Z minus X. So this will be 1. Next, the last one is R3 as R1 minus R3, R1 minus R3. A plus B plus C minus A minus B. C, P plus Q plus R minus P minus Q. Or X plus Y plus Z minus X minus Y is Z. Now, when you see here, second row, third row we have completed already. Now only left over first row. How can you do this? This is very simple. That is R1 as R1 minus R2 minus R3, which is equals to twice of R1 minus R2 minus R3. A plus B plus C minus B minus C. This is A. P plus Q plus R minus Q minus R is P. X plus Y plus Z minus Y minus Z is X. B, Q, Y, C, R, Z. So, which is nothing but RHS. I hope this is clear to everybody. Now, let me move on to sixth problem. That is, show that the given determinant is equals to 0. Now, here it is asked that you have to use the properties of determinants. So why do we use the properties? To make our simplifications easier. When the simplifications becoming harder, even applying the properties, you can do it directly also. There is no issue. Now let me see the sixth one. When we apply the property without applying the property, let me see both for the sixth problem. That is, sixth one is prove that 0 A minus B. Second row is minus A 0 minus C, and third row is B C 0 is equals to 0. By using the properties without using the properties, directly expansion, both the methods, let me see it. Now here LHS is equals to 0 A minus B minus A 0 minus C B C 0. Now what I can do is, when I consider two rows, any two rows, either first and second or second and third, or you can see first and second columns or second and third columns, whichever way you wanted to prove, you can prove it. Now what I do here is, I will consider first row and second row. When I consider first row and second row, in this element, one element is 0, so I cannot do anything. Here also one element is 0, I cannot do anything. Now what I will look up these two elements. In these two rows, I will look up these two elements. Now to make 0, what property I can, that means what kind of simplifications I can. Now the thing is here, first one, if I multiplied by C, if I multiplied R1 by C, I am concentrating only this one. By C, I will get minus BC. If I multiply by B, here also I will get minus BC. So this is just for understanding purpose, multiplying by C and multiplying by B. When I multiply by C, this will become minus BC, and here it will become minus BC. Both are minus BC. So that means I have to subtract. So what I do is R1 as C times of R1 minus b times of R2. Just by saying this, like elementary row transformations, what we have done, the operations for the elements, the same thing I am repeating here. Now, when I do this, what is happening here? So, can I apply such kind of operations? 100% by using the last property. If you apply Ri as Ri plus lambda Rj, that means Ri plus lambda Ri, or so just I repeat this, Ri as Ri plus lambda Rj, or you can write it as mu Ri plus lambda Rj. It is one and the same only. When you apply such kind of operations, the value of the determinant remains unchanged. Value will not change. Now, let me come to it, which is equals to C into R1, this is 0, minus, this is C into R1, C into R1 0, minus B into A, that is minus A into minus B is plus AB. Next, come here. A, this is C into R1, C into A, that is CA. I hope, are you getting clear? Next, CA minus B into RT, this is 0. Next, this becomes C into R1 minus BC minus of, this is minus B into R2, that is B into R2 is minus of minus BC, minus of minus BC, this becomes plus BC. Now, this is second row as it is, we are not touching, and BC 0 minus BC plus BC gets cancelled. Now this becomes AB, CA 0 minus A 0 minus C, B, C 0. Now in this, by taking A as common in R1, by taking A as common, by taking A as common in R1, we will get A into B, C 0 minus A 0 minus C, B, C 0. Two rows are identical. When two rows are identical, A into 0, which is equals to 0, since R1 and R3 are identical. So which is nothing but RHS. Which is nothing but RHS. This is one of the way by using the properties. Or don't use any property, or LHS is equals to 0 A minus B minus A 0 minus C B C 0. By expanding through R1, just simply expand it. 0 into anything is 0 only. Next, minus, because this is plus, minus, plus. So, minus A into, by leaving the corresponding row, corresponding column, minus A, minus C, B, 0. Plus into minus, that is minus B into, by leaving the corresponding row, corresponding column, minus A 0 B C, which is equals to minus A into 0 minus BC plus BC. This is minus B into, this is minus AC minus 0, which is equals to minus ABC plus ABC is equals to 0. So by using the properties, this is directly by expanding. So I hope this is clear to everybody. Next, let me proceed to seventh one. Now, the seventh problem as well as 14th problem, 7th problem and 14th problem runs on the same lines. There will not be any change. So 7th one I will do, 14th one on the same lines. If it is possible for you, you try to finish off. If not, put me a message so that I can do it. Now come to 7th one. You have to show that the determinant is equals to 4a squared, b squared, c squared. That means everything it must be in terms of the square. But here, when you see here, everything is not in terms of the squares. So what I do is, so LHS is minus a squared, ab, ac, bc minus b squared, bc, ca, cb minus c squared. Multiplying or 1 by a or 2 by b and or 3 by c. Because determinant is a value, if you are multiplying, compulsorily you have to divide also. It is not like elementary operations. Because there it is a matrix, here it is a determinant. Determinant means it is like a number. Number means if you multiply with, value will go on change it. So what you have to do, when you are multiplying, compulsorily you have to divide also. And dividing by, so multiplying by a, by b and by c. That means you have to divide by a into b into c, which is equals to 1 by ABC. When you are multiplying by A, so this will become minus A cube, A square B, A square C. And here, when you are multiplying with B, B square C minus B cube, B square C. Next, here, when you are multiplying with C, C square A, C square B minus C cube. The 14th problem, same thing you have to do. Multiplying R1 by A, R2 by B, R3 by C and dividing by ABC. Or multiplying C1 by A, C2 by B, C3 by C and dividing by ABC. Both way you can do it. Now once you have done this, then what you have to do is, you have multiplied R1, R2, R3. Now while taking column, you do it different way. You do it differently. That is, this is BA. That is, taking common A in C1. Now multiplying rows. Taking common in columns. Taking common A in C1, B in C2 and C in C3. Then we will get, when you are taking A, B, C as common, and already we have ABC by ABC. Now here, when you are taking A as common, minus A square, B square, C square, and here B as common, that is A square minus B square, C square. C as common, A square, B square minus C square. I hope this is clear to everybody. Multiplying through rows, taking common through columns, or multiplying through columns, taking common through rows. So ABC gets cancelled. Now what we do? Now when you see this, we have all square terms only. Now our problem becomes very easy. Now A square is there completely in R1, B square is there in R2, C square is there in R3. So just take, by taking common A square in R1, b squared in R2 and c squared in R3, which is equals to a squared into b squared into c squared. This is when you take a squared in R1 minus 1, 1, 1. When you take b squared in R2, this will be 1 minus 1, 1. C squared when you take it 1, 1 minus 1. Now what you have to do, either you can apply the properties here or directly you can expand. That is, by applying R1 as R1 plus R2 and R2 as R2 plus R3, which implies a squared, b squared, c squared, R1 as R1 plus R2, that is minus 1 plus 1, 0, 1 minus 1, 0, 1 plus 1 is 2. Next, R2 as R2 plus R3, that is 2 minus 1 plus 1, 0, 1 minus 1, 0, 1, 1 minus 1. Now by expanding through R1, that is equals to a squared, b squared, c squared into 0 into anything is 0 minus 0 into anything again 0 plus 2 into det 2, 0, 1, 1. This is a squared, b squared, c squared into 0, 0. This is 2 into 2 minus 0. It is nothing but 4 a squared, b squared, c squared. So I hope you have understood. Now when you do the 14th problem, you have to follow in the same lines. There is no change at all. Now let me come to 8th problem. That is 1 det 1 a squared. 8th one. We have to prove that 1a squared, 1b squared, 1a squared, 1b squared, 1c squared is equals to a minus b minus c minus a. Now, I said one procedure, that is, if possible, try to make the elements of any row or any column as ones. Then our problem will become so easier. But in this, already it is given that first column elements are 1, 1, 1. Whenever the elements are 1, 1, 1, you try to make 2 ones as zeros. That's all. That's only the procedure. Try to make 2 ones as zeros. So how do we make? Either you can apply row operations or column operations. But in this problem, what operations shall we do it? So LHS is equals to 1a squared, 1b squared, 1c squared. Now we need a minus b. A minus b means, so this is R1 as R1 minus R2. So I make the operation R1 as R1 minus R2, and so I can do one more operation, R2 as R2 minus R3, R2 as R2 minus R3. So I get A minus B, B minus C. When I do this, 1 minus 1 becomes 0, again 1 minus 1 becomes 0, 2 ones becomes 0. Now shall I apply one more operation R3? Shall I apply one more operation R3 as R3 minus R1? Don't use, because maximum you can apply since it is 3 rows are there. So 3 columns are there, 3 by 3 means maximum you can apply 2 operations only. You cannot apply 3 operations at a time. So which is equals to R1 minus R2, R1 minus R2, 1 minus 1, A minus B, A squared minus B squared. R2 as as R2 minus R3. 1 minus 1, B minus C, B square minus C square. 1 C, C square. Which is equals to 0, A minus B, A minus B into A plus B, 0, B minus C, B minus C into B plus C, 1 C, C square. Now in R1, A minus B is there, in R2, B minus C is there. So take common by taking A minus B in R1 and B minus C in R2 as common, we get A minus B into B minus C into that 0, 1, A plus B, 0, 1, B plus C, and this is 1 C, C square. When two elements of any row or column becoming 0, so I can expand this determinant by using that row or column. Now here in first column, two elements are 0, so I expand this determinant by using first column. That is by expanding through C1, which is equals to A minus B, B minus C, 0 into anything is 0, minus 0 into anything is 0, plus 1 into, by leaving the corresponding row, corresponding column, 1 A plus B, 1 B plus C, which is equals to A minus B, B minus C into, this is B plus C minus A minus B. Here B minus B gets cancelled, which is equals to A minus B into B minus C into C minus A. Let me proceed to the next problem, that is the second case. Again it is 1 is there in the first row, so you have to apply the same procedure. What is that? You have to make two ones as 0, that is 1 minus 1, but here in the right hand side it is given A minus B, B minus A is there, so you can apply C1 as C1 minus C2 and C2 as C2 minus C3, so that in the first row you will get 1 minus 1 0 and again 1 minus 1 it is 0, so you will make zeros. So like the first case. Next, come to the ninth problem. So ninth problem again, this is given as x square yz, y square zx, z square xy is given. Right hand side again it is x minus y minus z. So this can be done in different ways. So one of the easiest method is what? X minus y is there, y minus z is there. So what operations you can? So like 8th problem, what operations can be? R1 as R1 minus R2. When you do R1 as R1 minus R2, you will get x minus y, x square minus y square and z into y minus x. In the same way, another operation is R2 as R2 minus R3. So when you apply these two operations at a time, you can simplify and finish this problem. Next, let me come to the 10th problem. That is 10th one. First case, it is x plus 4, 2x, 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 x plus 4, 2x, 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 x plus 4 is equals to 5x plus 4 into 4 minus x, 5x plus 4 into 4 minus x whole square. Now, let me say this. So that is LHS is equals to x plus 4, 2x, 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 x plus 4, 2x, 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 x plus 4. What is here? 5x plus 4. So how do you get 5x plus 4? Either you make C1 as C1 plus C2 plus C3, or you can make as R1 as R1 plus R2 plus R3. Whichever is convenient for you, you can go for that method. So let me take C1 as C1 plus C2 plus C3, which is equals to x plus 4 plus 2x plus 2x, 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 4x plus x, 5x plus 4. This is 2x, 2x. Again here, 2x plus x plus 4 plus 2x is nothing but 5x plus 4. This is x plus 4, 2x. Again, C1, that is 2x plus 2x, 4x plus x, 5x plus 4, 2x, x plus 4. By taking 5x plus 4 as common in C1, we get 5x plus 4 into 1, 1, 1, 2x, x plus 4, 2x, 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 x plus 4. Now the problem is almost over. Why? We have got 1, 1, 1. When we got 1, 1, 1, what we have to do? Just to make any two ones as zeros. So now here R1 as R1 minus R2. R1 as R1 minus R2 and R2 as R2 minus R3. We will get 5x plus 4 into, now this is 1 minus 1 and here it is 2x minus x minus 4 and here it is 2x minus 2x. Here it is 1 minus 1, x plus 4 minus 2x, 2x minus x minus 4. This is 1, 2x, x plus 4, which is equals to 5x plus 4 into 0, 2x minus x minus 4, this is 0, 0, x minus 2x, this is 4 minus x and this is x minus 4, this is 1, 2x, x plus 4. Now see, what actually we have to prove? This is 4 minus x. So 4 minus x means this is x minus 4. I can write this as minus of 4 minus x. So by taking common 4 minus x, by taking common 4 minus x, by taking common 4 minus x in R1 as well as R2. In R1 and R2 we get 5x plus 4 into 4 minus x whole square. So 4 minus x whole square, why I am writing? 1 4 minus x from R1, another 4 minus x from R2. Into that 0. This is 4 minus x minus 4, but we have taken 4 minus x, so this is minus 1, 0, 0, 4 minus x, another one x minus 4 is there, minus 1, 1, 2x, x plus 4. Now you can expand through either R1 or C1 by expanding through C1 5x plus 4 into 4 minus x whole square into 0 minus 0 plus 1 into that minus 1, 0, 1, minus 1, which is equals to 5x plus 4 into 4 minus x whole square into minus 1 into minus 1 is plus 1, which is 5x plus 4 into 4 minus x whole square, which is nothing but RHS.